If you haven't subscribed, ensure you do so. Two speakers are placed above and below each other, as in figure P14.40, and driven by the same source of frequency 4.5 times 10 to the power 2 Hz. So these two speakers are driven by the same oscillator. An observer is in front of the speakers to the right at point O, at the same distance from each speaker. So it is important to note that at the same distance from each speaker. What minimum vertical distance upward should the top speaker be moved to create destructive interference at point O? So that's our question. Then let's look at our diagram. Right. So this is figure P14.40. So this is a speaker here, and this is the speaker here. They are driven by the same oscillator. Then this is distance R2, labeled R2. Then this is distance labeled R1. So the observer is standing here at A. Then the distance from here to there, it's 8.00 meters. Then the distance, or the separation distance between this speaker here and this speaker, it's 3.00 meters. So we can tell that the distance halfway here means that going up there is 1.5 and going down here it's 1.5 meters. So with this information we have, it is important that we look at again the question. Okay, so the question says, at a frequency of 4.50 times 10 to the power 2 Hz. So this means the frequency it's 450 Hz. When you punch that on a calculator, 4.5 times 10 to the power 2, giving us 450 Hz. So that's our frequency. Then it is important to note that we need to calculate the wavelength first. So in this case, they haven't mentioned the speed of sound in air. So in our previous videos, we said, unless otherwise stated, the speed of sound in air is 343 meters per second. So if they have specifically stated, then we won't consider the speed to be 343 meters per second. But if they've not stated in the question the speed of sound, then we'll consider the speed of sound in air to be 343 meters per second. So in this case, they haven't specified the speed of sound in air. So therefore, we'll say the speed of sound in air is 343 meters per second. So with this information, we can calculate the wavelength of this sound wave. So to find the wavelength of a wave, we'll say velocity is equal to frequency multiplied by wavelength, which is given there. So we want to find the wavelength. So we make the wavelength the subject the formula. When we do that, we are getting the wavelength to be lambda is equal to velocity over frequency. The velocity we just stated that is 343 meters per second over the frequency, which is 450 meters, 450 hertz. That's the frequency. So when we punch that on a calculator, 343 divided by 450, we are getting our lambda, or the wavelength, to be 0.76222 hertz. So lambda in short can be written as 0.76, like that. So we have found the lambda. Then it is also important to find the value of R2. So at first, before the speaker is moved upwards, the top speaker, before it's moved upwards, the R1 and R2 are the same. So in this case, let's try to find that value for R1 and R2 before the speaker is moved, the top speaker is moved upwards. So to find the value of R2, we will consider this as a right angled triangle. So R2 in this case becomes the hypotenuse. Then we've said this distance there is 1.5 meters. Then the distance here is 8.00 meters. So this is the hypotenuse. So to find R2, we'll say R2 squared is equal to 8 squared plus L squared. So in this case, let's see. So this distance, we've considered it to be L. So that's where the L squared is coming from. So L squared, so L is 1.5, you square it. So when you square 8, you are getting 64. When you square 1.5, you are getting 2.25. So when we add this together, we are getting 66.25. So here, this square root, we want to remain with just R2. So this is why we have introduced this square root. So when we do that, we are remaining with, so the R2 is approximately to 8.14 meters. So this is the length for R2. So having done that, then it is important to also now consider R1, to find R1 then when the speaker is moved upwards. So what do we do? So let's look at the diagram once again. So let's consider this part of this diagram only. Let's consider that. So so I'll draw that diagram. So let's consider this. This is okay. So imagine this is our diagram, like this. Then this is R1, like that. So they're saying if this speaker here is moved upwards, so that will mean that when this speaker is moved upwards, then R1 becomes like that. So this will mean there will be this additional distance there. So this additional distance, we say it's x is we will name it as x. So to draw it properly, it will be like this. So we'll assume the speaker was initially here, then now it has moved to here. So we can tell that there is this additional distance x. So we'll say this distance here, the total distance here is 1.5 plus x. So this is the information we have so far. Right. So maybe we use this diagram. So when this speaker is moved upwards, so it will mean there will be a distance, there will be an additional distance. So at this point, maybe the speaker will be here. So you find that there will be an additional distance which we'll name as x. So I'm sure it's understood. So to find R1, we'll say we'll look when you look at the diagram, you are finding that looks like it's a triangle. It's actually a triangle. So to find R1, we'll say R1 squared, 8 squared plus the distance 1.5 plus that additional distance x. So we'll say 1.5 plus x, then you square it. So since we want to remain with R1, we'll introduce the square root both sides. So when we introduce the square root, this is what we remain with. So we say 8 squared is equal to 64. When you expand this is this 1.5 plus x to the power 2 can be written like this, in this format. So when you expand this is what you are getting. So you can add 64 plus 2.25, you are getting 66.25. Then you add 1.5x plus 1.5x, you are getting 3x. Then this x squared. So this is our R1. So that's the distance R1. So at this point, we can now come to our equation. So this is the equation for R2 minus R1 is equal to n plus 1 over 2 close bracket lambda. So this is the formula for destructive interference. Okay, so when n is equal to 1, then this formula can be written as that. Okay, so since now the speaker has been moved above or upwards, so that will mean R1. So this that will mean this formula will be written like that, because now R1 is larger than, or is R1 is bigger than R2. So say R1 minus R2 like that. So the lambda we have calculated to be 0.76. Then R1 we have in the we have calculated, or we have the expression of R1, which we said is 66.25 plus 3x plus x squared. So R2 we said it's 8.14. So we'll substitute. This is what we have substituted there. Then the lambda we have substituted with 0.76 over 2. So at this point we can make this negative 8.14 will cross the equal sign, will go to the right hand side. When that happens, we'll remain with this expression here and with that. So this will be added. So let's see what's next. So when you add 0.38 plus 8.14, this is what we are getting. Then we remain with this expression. So we want to remain with a quadratic type of, we can tell that this the expression inside the square root is a quadratic expression. So what do we do to remain with this expression? So we will introduce the square. So when we introduce the square both sides, the square and this will simplify, so we remain with this quadratic expression. Then 8.52 squared, we are getting 72.5904. So at this point, this 72.59 will be taken to the left hand side and it becomes negative. Okay, so when we do that, so we'll say 66.25. So what we will treat the like terms. So 66.25 and negative 72.5904 are like terms. So we'll say 66.25 minus 72.5904. So when we do that, when you punch that on a calculator, we are getting the answer to be negative 6.357. So at this point, we are getting the quadratic expression to be x squared plus 3x minus 6.357 is equal to 0. So at this point, you solve this quadratic expression, and the answers you find, you get the positive answer, which is x is equal to 1.43 meters. So that's the distance. So this the speaker needs to be, the top speaker needs to be moved 1.43 meters above for the observer at point O experience the destructive interference. So there will be an x value which will have a negative, so you ignore that one. So this is the answer, the final answer. Thanks for watching. Remember, subscribe to our YouTube channel.